And today, I'm going to guide you towards an overview and understanding of active galaxies. So, galaxies come in a variety of morphologies in the local universe. We have ellipticals, we have spirals, we have lenticular galaxies. Some of them are really, truly special. And what I mean by special is that some of them are characterized by much more light than what an ordinary galaxy would have. And these are called active galaxies. More specifically, they're called active galactic nuclei, AGN. Why? Because the nuclei of these galaxies are extremely luminous, so luminous that they can outshine the full integrated luminosity of the underlying galaxy. In fact, in many cases, you don't even see the galaxy, but you only see a bright spot coming from the center. And in fact, historically, some of the astronomers thought that they were not observing galaxies, but they were observing stars, single stars. So let's go and see what I'm talking about. What are these AGN? This is M87. This is an elliptical galaxy at the center of the Virgo cluster. It looks a normal elliptical. However, it's not. There is a huge feature coming out from the center of the galaxy. It's a jet. This feature is indicative that this galaxy is active. So what that means, there is something else generating power, in this case, kinetic power, responsible for the jet. Over here, you see a comparison of a normal galaxy, but you can see that these two galaxies are not truly identical. On the left-hand side, you can see that towards the center, there is a bright spot over here that is absent in the right-hand side. So we label the galaxy on the left as an active galactic nucleus galaxy, and this one, we label it as a normal galaxy. When you take the spectrum of a galaxy, of an active galaxy, I remind you, the spectrum is a plot, a diagram of intensity as a function of wavelength or frequency, you do see that the spectral behavior of an active galaxy is substantially, profoundly different from what you would get from a normal galaxy. On the top, you see the spectrum of a normal galaxy, NGC 3368. This is what you would expect from any type of galaxy. However, when you look at galaxies that are characterized by an active nucleus, and these are called usually, especially in the local universe, they're called Seyferts by the first astronomer who discovered them, you can see that their spectral behavior is very different from that of a normal galaxy. First of all, the difference is that the intensity, while here the intensity tends to drop at lower wavelengths, here at all wavelengths the intensity is always quite high. There is no clear sign of a drop in the intensity. And on top of that, you can see the presence of these huge emission lines. Emission lines are spectral features, these spikes okay, that are coming out of the continuum, and they can be either broad or narrow. So astronomers usually, especially in the optical, when they do optical measurements of the active galaxies, they define type 1 and type 2 AGN depending on if their emission lines are broad or narrow, respectively. This is the intensity of a quasar. What is a quasar? A quasar is a specific class of AGN that are very luminous. They are much more luminous, on average, than Cephers. And you can see it here quite clearly, because at any wavelength, the intensity of a quasar is still higher than the one of a Seyfert galaxy. These are other sources that are now usually characterized in the radio. These sources are still active galaxies, not like M87. They are still classified as active galactic nuclei, not necessarily because of their bright spot at the center, but because there are these jets, these powerful jets coming out of the galaxy. Now, just to give you an idea of the scales we are talking about, the galaxy over here is at the center, and these are the jets that are moving out of the galaxy at megaparsec scales. So thousands of times larger than the scales of the galaxy that are a few kiloparsecs at the center. So these are huge, huge powerful jets that can move outwards. These specific AGN that are characterized by jets are usually called radio galaxy, which is a different type of AGN, or at least AGN that are usually detected in radio bands. Martin Schmidt, in 1963, took a spectrum of a star. So what that means is basically these were the very first measurements of quasars, quasi-stellar objects. As I told you before, these AGN have a bright spot at the very center of the galaxy. And this can be, in some cases, so luminous to outshine the full background galaxy. In this example over here, which is directly retrieved from the very first measurements of Martin Schmidt, you can see that this is, in fact, a galaxy, but you cannot see the galaxy. You can only see the bright spot coming from the center. And this is the reason why the very first observations of these sources were not that clear, and the astronomers started believing that they were observing stars. This is the origin of the name quasi-stellar source or quasar. So this is not a star, it is a real galaxy that is also an active galaxy, and the nucleus is so powerful to outshine the galaxy. So the emission, the origin for so much luminosity is something else. It's not of stellar origin, but something else is producing so much power, luminosity, to overcome stars in the galaxy. Let's have a look, a broad overview of the AGN spectra. This is a typical spectrum. This is the typical spectrum of an average AGN, of an average active galactic nuclei. So this is luminosity as a function of wavelength, and you can see that an AGN is extremely powerful in all wavelengths, right? From radio to the gamma rays. If you were to compare this with the spectrum of a typical galaxy, the spectrum of a typical galaxy will die off over here and over here, while instead the spectrum of an AGN is much, first of all, it's much larger, much higher, and much wider than the spectrum of a normal galaxy, a galaxy that is not active. So now we need to ask, of course, the natural question is, where this extra energy come from? Where does so much energy in an EGN coming from? Well, it's not easy, of course, to answer that question, and the astronomers working on this subject took years to give a possible scenario for the generation of this energy. The very first observation that is a key to our understanding of the central engine that is creating, that is generating this energy, comes from the so-called variability. What is variability? When you observe a source for a given amount of time, its flux will vary on a certain time scale. It can be constant, of course, but it can also vary. Many AGN show variability. What that means, show a plot of this type in which the flux changes as a function of time. You can see this as years. And if you monitor a source repeatedly along the years, you can see some variability in its flux. So the flux is not constant, but it tends to vary with some periodicity. Why is this relevant towards our understanding of the central engine? Well, this variability has been observed in all wavelengths, especially in X-rays. As I said, I told you before, an EGN emits at all wavelengths, so it also emits at very large energies in X-rays and gamma rays. At X-rays, over here, people have seen that the variability, the time scales of variability is hours. So within the day, within a day of observation, you may see a single AGN varying in its flux, so luminosity per unit time on the receiver. This is a key fundamental observation that sheds light on the origin of power coming from an EGN. Let me show you why. For a source to vary in its flux, it means that each part of the source must be coordinated in a way to vary at all points its flux. Imagine to have the luminosity coming from the sun varying on a given time scale on your detector. If you see this variation on the flux, this implies that each part of the surface of the sun should be coherently varying with the other parts of the source, in this case the sun. But in order to have coherent information, coherent variation in each part of the source, that means that information has been shared, okay, within each part of the source. So information is, in this case, we are talking about light. Light travels at the speed of light, which is c. So what that means is that the variation delta t is the variation of your flux within that time scale of variation of your flux. You have shared information between each part composing your source. And this naturally leads to a scale. The scale is the product of the speed of light and delta t, the time, the characteristic time of variation of the flux. So X-ray variability is extremely important because it provides us with a sort of upper limit on the size of the region producing the variation of the flux, producing the flux and its variation in time. Look at this. If we actually do the maths, we find that this size is of the order, based on the variability of, let's say, 1 hour, which is the minimum variability that you observe in X-rays, you get sizes of the order of 10 to the 12 meters. Does this ring any bell? Yes, it does, because 10 to the 12 meters is of the order of the distance between the Earth and the Sun, which is about 1.5, 10 to the 11 meters. So much energy that I showed you before from the AGN, which is coming from the very center, but is so powerful to outshine the full luminosity of the background stars, is generated from a very compact region located at the center of the galaxy of the order of the solar system. So it's extremely tiny with respect to the size of the galaxy, yet it's extremely powerful. So whatever the engine is that is creating so much energy, it must be extremely tiny, extremely compact, but extremely efficient. So what can power an EGN? Well, let's think. Let's go through the thought process that actually astronomers went through in the first observations of EGN. What could it be? Could it be supernovae? So you might recall a supernova is the explosion of a massive star. It emits a lot of light. That is also extremely powerful. Maybe it could be that event that we see is one or more supernovae happening at the center of the galaxy. However, that is not the case because the luminosity of a supernova is yet not enough. Is below several orders of magnitude below, for example, what you see in a quasar. So this is 10 to the 9 solar luminosity. In a quasar is possibly up to 1,000 times more powerful. Also, the time scales are not the ones that you require for an event like an EGN. So, and it's really difficult to have 1,000 supernovae located just exploding at the same time at the very center of a galaxy. That's really unusual. So this is not really a plausible explanation. We need something else. What can that be? So astronomers quickly realized that the source of energy coming from an EGN must be of gravitational origin. So for example, we know that if you throw matter on a neutron star, which is a compact object, this generates some light. Of course, this is by no means enough to produce an EGN. So in the case of an EGN, you would need a very, very compact but very, very massive object similar to a neutron star that can generate energy in a similar way as a neutron star when you throw mass on top of that. So astronomers came up with the idea of a supermassive black hole. A supermassive black hole could be enough massive to generate the energy that you require in an EGN. Now, some of you might ask, how can a supermassive black hole, that by definition is very black, be the most luminous source in the whole universe, like a quasar? This is a very fair question. Well, in order to answer that, let's go back to Physics 101. If you have a ball, okay, over here, that is displaced from the ground by a distance r, this ball has a certain potential energy. Imagine now that the ground is a supermassive black hole. If you have a machine, some sort of machine within or around the supermassive black hole that can convert this potential energy into kinetic and eventually thermal or luminous energy, then you might be close to the solution to our puzzle. Our original question was, where does the energy of an EGN come from? So now, let's have a look at the concept of escape velocity. Suppose this is Earth, for example. This is of mass m. This is a satellite mass small m. This is orbiting at a distance r with velocity v. So you can, this is in equilibrium, so you can equate gravitational force, centrifugal force, and from this equality you can get out the so-called escape velocity. So what that means is that for this particle, for this mass to escape the gravitational pull of planet M, you will need a velocity that is at least larger than that. What happens if the same mass M orbits around the black hole? Well, you do find a very similar thing. If you replace V with C, you will find that the minimal, the closest region of space in which you can reach with that mass before being swallowed completely by the black hole is the so-called Schwarzschild radius. Bear with me, each black hole is characterized by Schwarzschild radius, that is, the closest that you can get before and still hope to retrieve some energy from the source before any particle disappears beyond the event horizon. And the Schwarzschild radius is proportional to the mass of the black hole, and the other two are just constant. This is the constant of light, this is the constant of gravitation. So the larger the mass of the black hole, the larger the Schwarzschild radius. This is the potential energy of a particle that is orbiting at a distance r from the black hole. Now, this potential energy is, by definition, gm over r. Now, if you are able to convert this potential energy into light in some ways, and I will describe what these ways actually are physically, you can hope to generate light. A particle that is orbiting around the black hole will be able to release energy until it reaches the Schwarzschild radius. Or let's say it reaches a region that is very close to the black hole. After that, of course, nothing can escape a black hole. But down to that region, all its potential energy can be converted into something that we can actually see from the outside. In this case, luminous energy, like L over here. The efficiency of this process can be up to 40%. This process is extremely efficient if you compare it with the efficiency of nuclear reactions in stars, like our own sun. The efficiency of those processes are orders of magnitude below the efficiency of energy that can be retrieved from the gravitational loss of particles going towards a compact object, a neutron star, or in this case, a supermassive black hole. So this is the reason why astronomers believed that the loss of energy of incoming gas, for example, going towards the black hole can generate so much energy that can explain the luminosity coming from an AGN. Let's go back to the AGN spectra. So as I told you, the AGN spectrum of an active galactic nuclei is extremely broad from the radio to the gamma rays. What is producing all this energy? Let me guide you to what astronomers believe is producing each section of the spectrum. Let's start from the accretion disk. This is the machine I was telling you about. So what astronomers believe that an active galactic nucleus, the very central engine of a galactic nucleus, is a supermassive black hole, a big dark object at the center of the galaxy that is accreting gas particles around it, but these particles are losing potential energy and they are organizing themselves because of conservation of angular momentum. They are creating a disk around the black hole. Now, this disk is transparent to energy. So there is friction within the annuli of the disk. So each annulus over here is creating friction with the neighboring annuli. And what this creates, this friction creates energy, which is radiated away as luminosity. There is the origin of this luminosity. This luminosity can be up to 10 to the 42, 10 to the 48 ergs per second. It is sufficient to explain the luminosities also coming from quasars that are extreme luminosities. This accretion disk can explain the so-called big blue bump. A large portion of the full spectrum of an EGN can be explained by the energy released in the accretion disk. So let me be clear over here. There is gas in the galaxy. This gas eventually will reach a supermassive black hole at the center, a putative supermassive black hole at the center of the galaxy. Because of conservation of angular momentum, this gas will create an accretion disk, and through friction over there, some of the potential energy and kinetic energy will be transformed into heat and eventually light that is transmitted away. And this light is a lot of energy that can explain a big chunk of our observed spectrum in an EGN. But what about the rest? What's producing this part of the spectrum and this part? The accretion disk will not be able to explain this part and this part. You need something else. So this is a very convincing model, but it's not enough. We need something else. So another part could be the so-called unobscuring torus. So astronomers believe that there is some additional structure around the accretion disk. This is the black hole, this is the accretion disk, there are some clouds over there, and then there is some accretion, there is a big donut of gas around the accretion disk, and what this donut does, it absorbs part of the light coming from the accretion disk, and it re-radiates this, so it absorbs the light in the UV and it re-emits it in the infrared. And this explains the infrared bump. So what happens is that part of this big blue bump light is absorbed and re-emitted in the infrared by the obscuring torus. What else? These clouds over here are responsible instead for the broad line regions that we saw before. You might recall in a previous slide I showed you that the spectrum is characterized by both narrow and broad absorption lines. Those broad absorption lines are most probably produced by light coming from these clouds that are traveling very fast around the black hole. And because they are very fast, they create these features around in the spectrum superposed on the continuum that is very broad. Instead, the narrow line regions, that means in the narrow lines that are observed in the spectrum are most probably produced by other clouds that are instead far away from the black hole, and these clouds are most probably responsible for these narrow lines. And so all of these features are what is characterizing type 2 and type 1 AGN. Last but not least, we have a jet. And this jet, people don't really yet understand the full details of jet production in AGN. But a large fraction of AGN show jets. And they are so-called radio loud because these jets can be observed in the radio wavelengths. And in many AGN, you see that they continue to be radio loud. What that means is that the emissivity, even in the radio bands, is extremely high, as you can see in this diagram, in the sketch over here. And this is most probably due to the fact of the generation of these jets. The generation of jets could be most probably linked to the magnetic field around the black hole that moves with a spinning black hole in the center. I would like to now ask the question, why do you think some galaxies appear active, so they show this bright nucleus, these jets, and why are galaxies, many other galaxies, normal? They don't show these features. So there are two possibilities. If we stick to the model of a supermassive black hole accreting gas, so the accretion disk, the torus, and all that stuff, we can answer this question in two ways. Either we can say that only some galaxies harbor supermassive black holes at their center, or we can say that all galaxies have supermassive black holes at their center, but only in some cases the black hole is accreting gas, and therefore the black hole is triggered and is creating that machine and luminous light, right? Which of the two is the most plausible scenario? Astronomers believe that most probably the scenario in which all galaxies have black holes is the plausible one. Why is that? Because now astronomers are able to observe black holes even in normal galaxies. And the way they do it is that even though the black hole is completely black, so what that means is that you don't see any active feature coming from that galaxy, they are still able to measure the presence of a massive dark object at the center of normal galaxies. For example, I would like to show you the example of our own galaxy. This is our own Milky Way. We do see the presence of a massive dark object. So this is let's say, the center of our galaxy, and this is the monitoring of the orbits of stars around the center of our own galaxy. The interesting thing that you see, look at this star over here. Look at the movement of the star. When it reaches this point, so this star is moving in an elliptic orbit. It goes slowly over here, but when it reaches this point, it speeds up. Can you see it? Look, the star goes down and then it speeds up again. So if you work out the dynamical conditions of this star, as well as all the other stars moving around the center, because over here, where the red cross is, most probably there is a supermassive black hole. In fact, you are able to retrieve a mass of 4 million solar masses. So we believe, based on the motion of these stars in the center of our own galaxy, that even though our galaxy is normal, there are no clear active features coming from our own galaxy, yet the galaxy, our own Milky Way, harbors at its center a massive black hole, a 4 million massive black hole, a supermassive black hole. Our galaxy is not special in any ways, so we believe that many more galaxies, in fact, possibly all galaxies, will have a supermassive black hole at its center. However, only in some cases, only in a fraction of them, at any given cosmic epoch, those black holes will be accreting gas and therefore shining as active galactic nuclei.